Thus far, we've been working at the level of a programmer who is writing applications. We've seen this in a high-level language in assignments 1 through 3, in assembly language in assignment 4, and now just a bit of machine language in assignment 5. Now we start to look under the hood, below these abstractions that we've been dealing with all semester, in all 3 of those languages, that allow us to make assumptions about our environment that, frankly, aren't actually true. So in this second downward tour, we'll dive into how a program interacts with the operating system, and in doing so, we'll demystify how it is that we can assume that we're the only program running on a machine, when we know that's not actually the case, and that we can assume that we have all the memory on the machine, again, knowing that isn't really the case. There's a lot of nitty-gritty systems details in the remaining 6 lectures of the semester. I'm not sure whether I'm more astonished that there are only 6 left or there are still 6 left. Much like the joke going around about how this was a leap year, so February had 29 days, March had 129 days, and April is on pace for 2,900 days. But maybe I just read too many beleaguered parent blogs. Anyway, a lot of deep systems details, but also a lot of fundamental ideas about abstraction and modularity that prove the high-level concepts we've been stressing all along are also fundamental importance, even at the lowest possible levels. In this lecture, we're going to start off with the process idea, from which most of the other abstractions flow, and thus the underlying genesis of the allusions to the application programs and their programmers. We'll also talk about exceptions. Note this isn't the same thing as Java exceptions, which are our first foray into how the OS really gets involved in our program's life execution. We'll start off, as I said, with the idea of a process. We've used this term for a while now, talking about your program when it's running, but if it's going to be such a core idea for all of our future study of systems, we should really be explicit about our terms. Your program is the result of the build process that we've talked so much about. When the linker finally builds the executable, this defines your program. If you change something and rebuild it, this is now a fundamentally different program. Even if you give it the same name, that's really not so much an updated version as a completely new program that by its very existence regulates your previously built program to be irrevocably lost. Perhaps that's too philosophical. The point here is that the program is the executable code that you've built that is ready to run. A process, on the other hand, is an instance of actually executing that program. If you'll permit me a nerdy take on this, it would be that the process is your program integrated over time. It's the summation of all the instance of that particular execution of your program while running. The state of the registers, the state of memory, the branches that are taken or not taken in the control flow, etc. When the process is running, it is sharing the computer's resources with many other processes at the same time. For instance, when you're running your process, you possibly have your program's code up in Emacs. Maybe I'm too optimistic that people ever got multi-window execution working on ARMLab, or naive that they even tried, rather than just coding locally and then SCPing everything up for every edit. In any event, you certainly have at least one other process running, your shell that invoked your program to execute in a process. And because all 140 students in the class are working on their assignments during the last 48 hours before the due date, not only are your processes running, but so are all your peers. Here's an example of some processes running on ARMLab, specifically infinitely looping processes and debuggers that your peers never killed off. For the OS to be able to differentiate processes, each one of these processes that's running at the same time has its own identifier, the process ID, called either PID or PID. For example, 10,882 or 92,684 in the picture above. When a process begins operation, it gets a PID assigned to it by the OS, and the PID has to be unique for all processes running at the same time, though they can be reused after that. Typically, they're assigned sequentially until they overflow back to small numbers at a system-defined limit. On our system, as shown by the command in the bottom, this limit is 98,304. Sort of an odd number, thrice 2 to the 15. The first several hundred are formally reserved to the OS kernel, and in practice the first several thousand are actually taken up by it, since the OS invokes a whole bunch of long-running processes before any other programs get to be executed. The PID is going to be an important property when we start to talk about running a program that invokes multiple processes. Yet, despite these potentially tens of thousands of processes running, each one of these processes can, if it wishes, operate under the illusion, the fiction, if you will, that it's the only process on the machine. If they can think of themselves as having the processor to themselves, they can have these two further abstractions, fictions even at the assembly and machine code level, which is really incredible because we thought we were super low level by the time we got down to the machine code. The first is the illusion that their own private address space, the idea that they get all the memory on the machine, or in fact, even more. The laptop I'm recording this on has 16 gigabytes of memory, which is a ton. But all 2 to the 64 addressable bytes that we've just been assuming our addresses to be, 00 through 16 Fs, are more than 1 billion times that amount of memory. And the second is the illusion of their own private control flow, their own dedicated hardware for their program counter, their P state, etc., and that will change only as their program advances through its instructions. But again, these are just illusions. Every process is sharing the physical resources with many, many other processes. Time sharing the processor, swapping in and out the register values, and co-locating their memory in physical memory. Let's break these two illusions down one at a time, starting with the one of private address spaces. This will just introduce the concepts for something we'll cover in quite a bit more detail next lecture. When programming at the application level, you think of memory as simply a huge array of bytes. And you think you're the only one using it for your stack, your heap, and all your other sections of memory. But as is developing as the theme today, that's an illusion. In reality, the machine may, or really will, have less memory. But that's probably okay. There will be huge portions of your virtual address space that's not in use at all. And even of the virtual memory that you do have in use, only some of it is physically sitting in physical memory. Some may not be in physical memory yet because it hasn't been needed yet, while other parts of your process's virtual memory used to be in physical memory but no longer are due to contention for the limited physical memory with other processes. When programming at the application level, the hardware and operating system completely insulate you from those details. You operate under the illusion that your addresses are real, when they're not, and that they are always accessible, when they're not. In fact, they are virtual and almost seamlessly translated in hardware, with the help of the OS, into a physical memory location. And in fact, that physical location may not be resident in physical memory at all. Further, we think of memory as 2 to the 64 separate addressable bytes, which is sort of true. But for efficiency, we only move data in and out of physical memory at the granularity of a page, which on our machine is 64 kilobytes. Yet, almost completely diametrically opposite, we also think of memory as one huge array, when in fact it's a hierarchy of different memories. We'll discuss this next time, but we've already seen 2 levels, tiny, blazingly fast registers and big, slow main memory. But there are in fact many other levels, several levels of caches between the registers and main memory, and some memory, as we see above, is swapped out and the data actually resides on disk. A central theme in memory management is how to make use of these separate storage levels in order to give processes an illusion of big size, fast speed, and universal access across the virtual address space. How does this get implemented under the hood? When you access a virtual address, something has to translate it into a physical address. And if there is no physical address, because it's not in memory at the moment, something has to stop what you're doing, go fetch it from wherever it is, and only get back to you once the data you're requesting is available in physical memory. The answer is that there exists a mapping from your virtual address to the underlying physical memory. This is called a page table. And if you access some location in your virtual addressing space that isn't already present in physical memory, the OS has to take over to get it into physical memory and update the page table before you can continue. That's called a page fault. So here's an initial example. The process is executing instructions one after the other. In the ideal case, you execute and every location in your process's virtual memory that you access is resident in physical memory. For each access, the CPU is going to look at the virtual address, calculate what page, again 64K on our machine, but system dependent and often configurable, what page of virtual memory the address is on, and check if that page is in physical memory. At least in principle. This means that we have to consult the page table for every single lookup. We'll see optimizations for this later. But in any event, once the CPU finds the physical page it's on, it does the memory access for the program into or out of physical memory. But sometimes the memory we want to access isn't in physical memory. Maybe it wasn't loaded at the start of the program and we haven't accessed it yet. Maybe it was accessed before, but it ends up being evicted since we last accessed it. In both cases, we need to get it back. The hardware generates a page fault, which is asking the OS to intercede on the program's behalf. The OS goes to find the data that the process needs, which since it's not in memory is stored on the disk, and then loads it into the physical memory. Note this may involve evicting something else to the disk. Once it's in memory, the OS returns control to the CPU to try the instruction again, this time under the conditions that it will in fact find the required address resident in the physical memory. So having seen that very brief overview of the separation between virtual memory that processes perceive and the physical memory in the hardware, here's a question to ponder. What effect does implementing this memory illusion have? Contrast both speed and security with a world in which you're interacting with the physical memory itself. Pause the video here, take a few moments to think about, for these two factors, whether virtual memory is good or bad. Alright, let's take these one at a time. Speed first. Virtual memory in fact decreases performance. There is overhead for going back and forth to disk, and it's particularly hard when many processes need lots of memory. As the processes share time, they return to a physical memory that doesn't have their data in it, and so it has to be read back from disk. And when we write the other process's data out, that again takes time, and when they come back to the CPU, they'll have to read theirs back in. This is called thrashing or churning, and it's problematic because it reduces execution time to that of disk access rather than memory access. And recall we're talking about orders of magnitude decrease in speed for each next level down the memory hierarchy. On the other hand, virtual memory does allow processes that have dramatically large data needs to run at all. It may be slow, but it's possible to swap in and out more memory than is physically available on the machine using the disk, even for a single process. Contrast with using the physical memory itself, we couldn't ever access more physical memory than we have. Now for security. Security is improved because different processes have the illusion of a private address space. So our addresses are distinct. Even if we're both writing to the address hex decaf, they're actually separate locations in physical memory, and so they don't interfere with each other. And furthermore, even if multiple processes have data in physical memory at once, no other process can read the other's memory, because it has no way to name it or access it. Furthermore, there are protection modes in the physical memory. So the correct answer is B. But next lecture we'll try to mitigate the red down arrow for speed. So again, keep that private address space in mind for next lecture when we really dig into the details of virtual memory. The second abstraction we'll talk about today is the illusion of private control flow, as though every instruction that the processor runs is for our program and our program alone. It's a fact that many computers these days have multiple CPUs. Each ARM Lab computer has 96 of them, in fact. To keep things simple, in this course we'll pretend that each computer has only one CPU, but all points that we make will generalize naturally to multiple CPUs. With that single processor, we perceive our process is running all the time, but of course that can't be. In practice, it must time share in tiny little time slices with all the other processes running on the machine. So some of process X's instructions will run, then some of process Y's. Sometimes this happens because one process doesn't need the CPU for a bit. For example, when there's a page fault, and it has to wait for the OS. Other times it happens because the OS actively comes in and tells it to share nicely with other processes. Particularly for interactive processes, each process has to get its share of the CPU relatively frequently to maintain the illusion of private control flow. There's one bit of vocabulary we need to define, because English isn't quite precise enough without a formal definition. Technically, X and Y aren't running on the CPU at the same time. But X and Y are said to run concurrently if and only if X begins during the lifetime of Y or Y begins during the lifetime of X. So at any given time, a process might be in one of several states. It might be running. The CPU is actively executing instructions for this process. It might be ready to run. The process has instructions that it could be running, but the CPU hasn't chosen to run this process's instructions at this time. Or the process could be blocked, in which case it's waiting for something else to finish on its behalf. For example, I/O. Again, as mentioned before, we typically talk about the CPU as though there were only one, even though it might be more appropriate to use the indefinite article like we did in the bullet points on this slide. So let's think about a DFA for these states. The OS implements transitions between the three statuses. A process becomes ready to run, and the only state it can transition into is running, because it can't request a blocking operation without being in the running state. So the OS will eventually determine that it's the process's turn. It will transition from the ready state into the running state. It will run for a while, and then either execute an operation that blocks, for example, a request from the OS like a page fault or I/O, in which case it will transition into the block state, or it will run for long enough that the OS decides it's run long enough and the others need to run, in which case it is back to the ready state. In the block state, eventually the service a process is waiting on will have finished, and now it will be able to run whenever it's next picked to do so. Thus, it will transition from blocked into ready. Having described the concept of a process status and seen the state diagram, we can now look at a more detailed version of the previous diagram that throws in a temporal element. If this switching is done on a small enough timescale, each process can still maintain the illusion of being alone on the machine. Additionally, work is sometimes done on behalf of your process even when it is not resident in the CPU. For example, when the process has the CPU, it may invoke instructions to send a bunch of data to a sound card. And then the sound card's driver process, or an embedded processor, may be able to continue playing that data. It seems like it's coming from our process, even when our process is no longer running. That means the listening user won't know unless the process is stuck in the ready state for so long that all the previously sent music is played. This is unlikely, as context switches occur anywhere from 50 to several thousand times per second, depending on system specifications and load. That leads us into a discussion of how this switching between processes actually works. Let's move down one level, from the black box of a process to the individual components that make up a process's state. We call the state of a process its context. This is the contents of memory, the contents of registers, even including special ones like PC or pstate or SP. This is everything the OS needs to know in order to manage the process. Certainly, we will have to restore all the registers to be used by the instructions as we restart from a context switch. But if you think of this, it's not unlike a function call, where before we seed execution, we have to store away the persistent data into locations where they'll be able to be restored when our execution returns. But rather than just the call or save registers, we'll have to store away absolutely everything from our context. Whenever the OS moves process X out of the running status, it must do a context switch. This involves saving the context of process X. It saves the context of registers and, in principle, all of memory. This saves the current state of the process. It's then ready to load the context of process Y, restoring its state. That means loading the contents of all of its registers and, in principle, all of memory, to exactly what they were at the time when process Y was last preempted. You can imagine there's a trade-off here. If we give processes large time slices, we risk having other processes starve for the processor, which would break our illusion of private control flow. But if we have too small time slices, we waste a lot of time saving and restoring context when we could have been doing useful work executing instructions. Now that we know about context switching, a natural question arises. Where exactly are the contexts for the processes that aren't running saved? The answer is a data structure kept in a special area of the OS's kernel memory. The data structure, called the process control block, is the full specification of a process in the operating system. This is the data structure of all the context and metadata that the OS might need to manage the process. The OS has one PCB for each process, and correspondingly, each process has a single PCB. When the process is created, the OS allocates a PCB for it, typically from a persistent pool of these data structures. The PCB's information is updated on each context switch, and when the process terminates, the PCB is returned to the OS's pool to be reused by another process. I've just said that this is a data structure with all the context and the metadata that the operating system might need to manage the process. In particular, it includes the PID, the status from the DFA we started by talking about, where in the process hierarchy this process falls, namely what's its parent and what children does it have. We'll talk lots more about parent and child processes later in the services downward tour, leading up to assignment 7. The PCB also records the process's priority. How often should it regain the CPU? Should it get to keep it for longer, etc.? And some historical data of its execution, as well as the entire context, as was the motivation to start talking about the PCB at all. As you can imagine, storing the context for process X and restoring the context for process Y could be quite expensive. It's overhead when you're not running either of those processes themselves, and it takes up memory in the OS. Surprisingly enough, though, it's not so bad, partly thanks to a recurring theme. The virtual memory concept that we've just seen today, we will find pervades the design of all modern operating systems. In this case, the context switch mechanism relies on virtual memory. We don't need to save away the actual memory contents because it's either in physical memory and will be saved when it's evicted, or it is already swapped out to disk. So that was the data, and the page table data structure maintained by the OS on page faults for our process has all the metadata for our process's memory. The OS just has to switch which process's page table that it and the hardware will be using. Again, more on this next time. Context switching on a computer that does not implement virtual memory would be a very expensive undertaking because there would be no mechanism for sharing the physical memory. It would instead be like the entirety of physical memory has to be evicted on each context switch. So now that we've seen that the OS implements preemption by doing context switches, let's go one level lower. How does the OS implement those context switches? The rest of this lecture will detail a variety of categories of exceptions. That is, a variety of reasons and ways that a process might have to stop executing, either temporarily or permanently. An exception is an abrupt change in the control flow, along with a process's state. Normal flow of control is sequential, but we have seen several statements in C that can change it. For instance, if, switch, while, do, for, go to. We've also seen several instructions in assembly language that could change the control flow. Unconditional branch, branch and link. There are other mechanisms that change control flow in more exceptional ways, which, as the English word suggests, are related to some disruption. Before we get into the details about exceptions, I should disambiguate the term from where you've perhaps seen it before in the context of programming. The Java programming language uses the term exception to describe the mechanism implemented by try-catch and throw statements. Those statements indeed do implement a kind of exceptional control flow, but OS people tend to use the term exception to indicate lower-level mechanisms, not the special Java objects managed via try, catch, and throw. Some exceptions are what we call synchronous. They occur directly as the result of an instruction your process is executing. For example, when your program calls getChar or printf, and thus you need to interact with an I/O device. Doing so is a privileged operation, so you have to cede control to the OS to do it on your behalf. In this case, you'd trigger an exception in your own code to ask the OS to perform some service for you. The category of functions that makes these requests for the OS to take over for you is referred to as a group of system calls, and we'll see a bunch of them throughout the rest of the semester. Another example of a system call is requesting that the OS move your program break in order to give more memory to your heap section so you can allocate more dynamic memory. We'll see this in much greater detail in Assignment 6. Other exceptions, though, might not be by design in your program. For instance, division by zero is an instruction in your program, but the intent of that division instruction is, presumably, not to generate an exception. Similarly, when you access memory that isn't in physical memory, this generates a page fault. We mentioned this earlier. Again, this is caused directly by an instruction your process executes, but it isn't itself the intent of the instruction. There are also exceptions that are not caused directly by the instructions that your process executes. These are asynchronous instructions. These are caused by things happening to your program, outside your control, that may impact whether your program is put back into the ready-to-run state while executing, or if in fact it can re-enter the running state on a CPU from the ready-to-run state. Examples here often involve hardware interaction. The user presses a key, the disk signals that it is finished, or a trigger by the CPU itself. What happens when an exception occurs? Your process is running happily, an exception happens, whether triggered by you synchronously or by something else asynchronously, and the OS takes over. It may run for a while, doing something in response to the exception, and eventually return control to your running process having handled the exception. Or indeed, for some exceptions, they are so problematic that they're fatal and you never get to run again. Earlier, we compared context switches to function calls. And here, when the OS steps in to handle an exception, this is indeed similar to a function call. The flow of control changes at a point, other code begins executing, and at some other point later in time returns to some instruction in the original code. But it isn't exactly the same. The CPU has an additional job of saving data for the OS, not your own program manipulating its stack. And the handler runs in an elevated privilege mode, often referred to as kernel mode, in which it can change the page table or access the disk or the keyboard. Your application code has abstractions to reason about these operations, but it doesn't in fact do them directly. The handler in the OS actually does interact with these devices more directly. Finally, whereas a function call will, assuming that nobody messed up any of the saved copies of X30, return to the very next instruction in the text section after the function call, an exception handler may return back to the current instruction again, or to the next instruction, or not even at all, depending on what type of exception occurred. To differentiate the purpose and behavior among different exceptions, we're going to subdivide them into 4 categories: interrupts, traps, faults, and aborts. We'll take them one at a time. The first one we mentioned earlier is the class where something asynchronous happens that has the outside world interfere with the execution of your process. It could even be a good thing, like the running process getting input from the user. In this case, the program execution gets interrupted so that it can be notified about something that happened on an external device. Here, the external device sets a pin on the CPU saying it has an urgent need to communicate with your process, and then the CPU will recognize this need to stop running your user process and let the OS handle that interrupt, and then return to your running process. The second type is a trap. This is the case that's perhaps the most familiar to us. It's synchronous, so directly caused by something your program does, and it looks just like what happens in a function call. This is intentional. System calls look exactly like other functions you can run, it's just that they're functions only the OS is allowed to implement. So traps are really intended to provide a function call-like interface to the OS, and so they are what happen when you make a system call, down to where it returns to your program at the next instruction. The third category of exceptions is faults. This is a synchronous exception that indicates an error has arisen from executing your instructions. This is something that needs handling, such as dividing by 0, or accessing memory that isn't loaded into physical memory, or indeed accessing memory that can't be accessed at all. So this is like a trap in that your program causes it, but unlike a trap where your program directly asks the OS to do something for it, here your program is inadvertently entering into an error state that it then needs the help of the OS to get out of. Note the error here isn't necessarily dramatic to the long-term running of your process. Consider a page fault that we saw earlier. This is an error, as the hardware doesn't know where to go to get the data you're accessing. But it's not really a problem because the OS can go and tell the hardware where the data resides, and thus how to get it back into physical memory. And so once that happens, the OS can return control to your program happily. Note that this will require returning to the same instruction in your program, since that instruction didn't finish successfully the first time. Other faults, though, will end up not being recoverable. For example, accessing memory that the program will never have access to, like trying to write to address 0. Unlike for a page fault, for a segmentation fault, there's nothing the OS can do to help out the hardware to recover from this error state. So the default handler is just that the program will crash and the process will terminate. Finally, the fourth category is aborts. This is an asynchronous exception in which the hardware determines that an unrecoverable error occurs that the OS can't possibly bail you out of. The CPU overheating, physical data corruption, etc. Your process isn't at fault and it can't possibly continue running. We won't really be concerned with aborts because there's nothing we could do about an abort anyway. So here's the table that summarizes our 4 classes of exceptions. Interrupt is the only one that's truly asynchronous because it is an external device that triggers it. And once the OS has handled it, it will return to the next instruction we would have been moving on to without the interruption. Traps are synchronous, deliberately arising from our program requesting OS services via a function call. Once the OS does what we ask, it will return to the next instruction so that we can continue with our operation having been successfully served by the OS. Faults are also synchronous, but arise inadvertently from our program. So here we're going to return to the exact same instruction and try again. The hope being that in the meantime, the OS has been able to do something in its handler to rectify the error and make it possible that the instruction will succeed the second time. Of course, it is possible the OS wasn't able to recover and it won't end up returning successfully to retry the instruction. And finally, aborts are fundamentally unrecoverable errors that will terminate your process without ever returning to it. The other exceptions happen without your knowledge, and as a programmer we don't see these. But since traps are things that your code calls to ask the OS to intercede, this is something that the programmer will be concerned with. So let's talk about them in a little bit more detail. There are a lot of different requests we can make of the OS, each one indicated by a number. The mechanism, as we've said, is very similar to a function call. And it is even at the assembly code level. We're going to pass data as arguments into the trap handler in registers x0 through x7. We're going to supply x8 with the number that indicates which trap operation handler we want the OS to execute on our behalf. Because this isn't a regular function call, there's a different instruction to make it happen. The mnemonic is supervisor call, and the ARM instruction is SVC. By convention, we always use SVC0, and the immediate value is always 0 and it's always supposed to be ignored, but it's there actually as a remnant of an earlier version of ARM in which, rather than using X8, the immediate value was used to indicate the trap operation. Fortunately for you, perhaps, we're done writing assembly language for assignments in this course. So when in assignment 6 you have to change the size of the heap, you won't need to work at such a low level. Instead, you'll execute traps by doing system calls. In this case, calling the system level function break, that is a function wrapper around the instructions for trap 214. As the appendix to this slides, there is a listing of a bunch more system call functions that you might end up invoking through the rest of this course. So now we know a lot more about exceptions. That means we can continue to make our earlier discussion of context switches more and more explicit. Here's an updated version of our temporal diagram with process X and process Y running concurrently. Process X runs for a bit, and eventually there's an exception that happens, either synchronous or asynchronous. The OS intervenes, and then perhaps uses that as an opportunity to let process Y run, if process X is waiting on a completion from the disk, or maybe it just ends up that at the time of that exception, it was the end of X's time slice. Likewise, eventually Y will have an exception, and the OS will intervene, and perhaps another context switch will occur. So we think about exceptions as being, well, exceptional, but they're actually frequent. It's super common for a process to trap to the OS to request help. It's super common for a virtual memory page that might be accessed not to be resident in physical memory. And further, even if none of these things occur, there's still a hardware mechanism to generate an interrupt to expire the current time slice. That allows the OS to run very briefly and decide to perform a context switch. So we've seen two fundamental systems concepts today: the process abstraction, which is an instance of a program in execution, and the control transfer concept of an exception, in particular 4 different varieties of them. This is the end of the narrated lecture content, but I do encourage you to take a look at the slides after this point, which provide a simple control flow with traps, interrupts, and faults, and then the appendix I mentioned earlier with a listing of common system level functions.